Okay, so let's begin with the Taylor-Macol equation, which we said that we will solve by Runge-Kutta method, right? Okay, so let me write this down. Okay, so this was primarily the main task. Okay, when we tried to solve when we try to solve the flow past the cone, right? Okay. Okay, so this was essentially the equation 6. So we and if you remember, right, so right, so this was the unknown, this was the non-dimensionalized form, which is v dash here, right. Okay, so this was our Taylor-Macol equation, which we needed to solve numerically. We can't solve this in the closed form in order to get the solve for the flow when past a cone, right. So, okay, so we said that this is an equation which has basically just if you look here, just one unknown, which is VR dash, right. So, if we are able to find VR dash from here, then we should be able to get the rest of the properties, which is V theta dash, and then correspondingly the thermodynamic properties. Okay, so okay, let's begin. So let's say here, okay, okay, now this y out here is just a parameter. It's just a parameter. It's a dummy variable, so to speak. Okay, so let's say dVr dash d theta is equal to y. If we do that, then what happens to this equation 6? So this was equation 6 as we derived it. So therefore, what we get, you can see from here itself. Okay. This, and then let's take this on the right hand side and write that as right. So we have this out here. Now, if I work with this out here, then I will write the from here. So from this equation, then I will write it like this. Okay. just rearranging the variables. Right. So, just rearranging the variables from here. So, I am just writing this out as d y by d theta as in this form. So, what you can see basically is that this is essentially a function of, if you see over here, right. So, this is a function of y and theta, or what we can say is basically is I can write this, that y dash, if I write this in here, and this is the first derivative. So, y dash is basically a function of y and theta. Okay. Now, so now what we are going to do out here is solve for Vr dash, right. So, now what is the Runge-Kutta method? Okay. So, if you are not familiar with it, I will sort of just walk you. Okay. If you do not have any idea of what Runge-Kutta method is. So, let me just walk you through the procedure, and I think I would suggest that consult any standard textbook for what this method is all about. Okay, and you should be able to figure it out. Okay, it's pretty straightforward. Okay, so essentially what we're saying here, let me just write out what this Runge-Kutta method is, right. So, what we're saying is that, say in some space out here. Okay, so if I discretize my space at various points, right. So, at a particular point, say say I plus 1, right, then this value is actually given using the Runge-Kutta method as so, right, which is the value, okay, at the point I, okay, and you add to that this. Okay. So, now, so essentially let me just do this over here. Okay. So, I have, say, some domain like this. Let us call that this is I, okay, and these are all equal divisions. Okay. So, say here, and this is my point I plus 1. Okay. This is also H. So, what I am saying here is that the function value at I plus 1 out here is equal to the function value at I plus this out here, okay, this, and H is the space length, okay, discretized space length. Now, where in this particular case, since we have the y dash is a function of y and theta, and so here, so it's a function of theta I and y I. So, this k1 is essentially the function of theta I and the function at the point I, out here. Okay. Okay. So, in this case, of course, as you can see, we are differentiating over theta, right. So, this h, so essentially this means that theta 1, then theta 1 plus delta theta, theta 1 plus 2 delta theta, and so on and so forth. So, this is essentially we are differentiating over theta, right. So, if I go from say, so when I am calculating the value of my function here at I plus 1, okay. So, k 1 is the function at I, at the location I, okay. Now, k 2 is the function value at theta I plus half h, okay, and y I plus half k 1, okay, k 1 which I found out here into h, okay. So, when I say theta I, okay, theta I plus half h, what do I mean? So, theta I is here, this is my theta I, right. So, half h is over here. Okay. So, what I need to do here is calculate the function at the point not theta I, but here, but at this point, okay. And correspondingly the y function comes out to be y I plus half of k 1 into the into h, okay. This is k 2. K 3 is equal to okay. So, similarly k 3 is again theta I plus half h, which is here, but the y I is y, the y part is y I, okay, plus half of k 2 into h, okay. And k 4 is of course the function at okay, k 4 is the function at theta I, okay, plus h, which is here, okay. This is the theta and the y is y I plus k 3 into h. So, this is what the Runge-Kutta method is all about, okay. So, we are basically moving in step here in the theta direction, right. We are moving in step in the theta direction. So, and this is how we are going to go about it, okay. All right. So, if we do that now, let us see for our particular problem here, how does this work? Okay. Now, so how are we going, what is this theta in this particular case? Now, if you remember what we did last lecture, so essentially what we have is that this is our cone, right, and we have a free stream which is coming in, right, and so this is our shock wave. So, this is our shock wave. So, this is theta s and this is our surface, which is theta c. So, what we are doing here is essentially moving from theta s to theta c, right. We are moving from here to here. So, so our steps that I show over here are basically we are moving from one theta to the next theta to the next theta and so on and so forth, right. We move away from the shock towards the surface of the cone, right. So, let us start, okay. So, okay. So, at this point, okay, okay, and let us call this as Okay. So, so this is known here, right? At when we start here, when we start, this is known to us, V r r dash. So then here, therefore, right, this is also known, right, and let's call that as, okay. So let us start from this theta out here, this theta out here, okay. So when we start from right at the shock, so we basically know V r dash V theta dash, okay, if we start from there. So therefore, now, so essentially what we are saying here, what we are trying to do here is that so on and so forth. So on these radian lines, so this is my theta s. So this is, say, theta s minus delta theta, that is theta s minus 2 delta theta, this is theta c. So obviously, the more number of thetas you take, the the more number, the more of the properties one will be able to calculate. Okay. So if we do this, so starting here, right. So basically what we are looking at, for example, say y I plus 1 is essentially the function value at this radial location, right, at theta s minus delta theta. Okay. So starting here, so if we started over here, so let's say this is my I. So this is I, so let's say this is I out here, okay. If that's I, right, then K1 is a function of this, right. So now in here, so if this is so, in this particular case, this theta I is nothing but theta s, right, and yi is as we have over here, okay. So if we do this, okay, so this is what we do, and now okay, so let's say over here, let's call this particular equation, let's call this as 8, okay. Let's call this as 8. So if you look at this particular equation over here, okay. Now I know the function value, okay. I know the function value at theta s, right. So v theta s, and v r dash is known, right, at theta s, and y again here is v theta dash, right. So which is also known. So therefore this is the function value, this is the function value at y I, right, and theta is equal to theta s, okay. So so basically, or y at theta s. So this is known. So now one can calculate this. So this is also therefore known, okay. Using equation 8, okay. Did you get that? Okay, let's say that one more time. So what we're doing here is starting at this at near the shock, right. The angle there is what? Theta s, and correspondingly the y yi or dvr dash d theta, right. Dvr dash d theta is let's go back here. Yeah, so this is my y, you remember. So this is the y, which is dvr dash d theta, okay. So dvr dash theta, which is the y, is v theta dash. This is also known, this is also known to us. So if you look at this function here, which is y dash, right, which is y dash, vr dash, vr dash, vr dash, vr dash, all of this is known, right, at theta s, and y at theta s, or yi in this particular case, and yi, and yi. This is also known, right. So, yi is d Vr dash d theta, which is v theta dash. So, this is also known. So, you can basically calculate this particular expression, right. So, you can calculate the function value, which we calling as y dash. This is the function. This is known at theta s. So, therefore, and that function value. So, what we are doing here is that calculating the function value at theta s. Okay. So, which is known basically using, or this is the say function value actually. Function value at theta s. Okay. Okay, so if I do that, let us go ahead and yeah. So, let us say in this particular case, let this be this delta theta be 4 degrees. Just say it is 4 degrees. Okay. This is just for our calculation purposes. So, let that be 4 degrees. Okay. So, if I do that, okay, if I do that, so in this case, so therefore, just from the mathematics point of view, here what we said is that we will be moving forward. So, when we write this formula, right, when we write this formula, so to speak, this theta I plus 1 is ahead of the I, right. In here, however, when we are doing this, our I plus 1 is actually we are going behind it, we are going back. So, what only thing is the h here we will just write as minus delta theta, right. We are sort of moving back from here to here. Okay. Now, if I do that, then yeah. So, therefore, okay. So, now again, let us see. Yeah. So, when we come here, so here, so I plus half of h. Okay. So, theta I minus half of h. So, what we are going to now do is try to calculate k2, right. For k2, so we have I plus half h rather, right. So, this is basically equal to theta s, right, minus half of delta theta. Does that make sense? Okay. So, which means theta s minus 2 degrees. Okay. Theta s minus 2 degrees. Okay. And so yi was v theta s, right, v theta x minus delta theta is 4. So, we can write this, or basically what we can write this as so yi plus half k1 h, right, yi plus half k1 h is this, right. So, now what we need is essentially the function. Okay, what we need the function value, which is k2. So, k2 we need the function, okay, at theta s minus 2 degrees, and the y value Okay, does that make sense? So, let us just go over this one more time. What we did out here is that this theta, what we are trying to do here is calculate this. So, say let us call this as A. let us get down to B. Okay. So, we calculated K1. Okay. Now, we come to the K2. We come to the K2. For this, what we need to do is locate the theta, which is this, and also calculate the corresponding y, which is this, right. Now, so theta I plus 2h, okay, is essentially in this particular case I, okay, minus half of h, which is minus half of delta theta. So, this is the theta s, okay, theta I is theta s minus half of delta theta. So, basically what we are doing is we are going from here, right, we are going from here and coming halfway, we are coming halfway, right, which is what we have done over here, minus half of theta, which is theta s minus half into 4. So, we have just taken 4 here, just let this be 4 degrees here, okay, for this particular purpose. And then y I plus half of k 1 h. So, y I, which was known, which is known actually, is v theta s, right, v theta s minus half of k 1 into 4, and k 1 is what we have calculated in step A, right. So, therefore, v theta s minus 2 k 1. So, therefore, my k 2 now, okay, becomes the function at the theta value theta s minus 2 and the y value v theta s minus 2 k 1. Now, k 1 is something that we have already calculated, and theta s minus 2. So, now what we do is come back in here, and if you look at this function value, okay, so y here and y here and y here and y here are these new values, which is at this particular value, which is v theta s minus 2 k 1 and theta is minus 2, okay, and we put that in here. So, we get the function value at y and theta, everything. So, v r dash still remains the same. So, when we go here, so therefore, now we are able to calculate again using, so we calculate again this using 8. We put that in and we calculate this using the equation 8. Okay. So, let us go forward again. So, k 3. Okay. Now, k 3, or let us just say so what we need now, k 3 is essentially, right. So, this is the same as this value here, which is equal to, right. Now, y I okay. So, this is essentially y I was essentially v theta s minus 2 k 2. Okay. Now, k 2 is known from from this calculation out here. So, therefore, what we need is that k 3 is the function value at theta s minus 2 and okay, again using equation 8. Okay. So, you come back in here. So, using the same theta, just change the y, okay, change the y values here, and what we get is the function value. So, we get the function value at theta s minus 2 for v theta s minus 2 k 2. Okay. Finally, what we need is for k 4, right. So, then we get theta I plus h. So, theta I plus h is essentially theta. So far, we calculated two values at the midpoint over here. So, theta minus h is this. Okay. So, theta. So, this is nothing but theta s minus delta theta, which is theta s minus 4 degrees, right. This is it, and then y I plus k38. So, this is again y of I, which is v theta s, okay, minus 4 into k3. Okay. So, then we get our next the arguments. So, theta is essentially theta s, okay, minus delta theta, which is this. Okay. So, now basically the k4 is essentially this radial line, okay, this radial line, and the y out there is v theta s minus 4 of k3 which we have calculated in c. Okay. So, therefore, k4 then again becomes the function which is theta s minus 4 degrees, okay. Again we get this from equation 8, okay. We get this from equation 8. Okay. Now, having done this, therefore, now we can get the function value at the radial line theta s minus delta theta, right. So, therefore, our function value now becomes, okay. So, well, I mean, this is, let's say write it over here, okay. So, therefore, our function value at theta s minus delta theta, or say minus 4 degrees here, okay. Theta s minus 4 degrees here is equal to y of theta s, okay, plus 1/6, okay, of k1 plus 2 k2, okay, okay, into h, which is minus 4. So, okay, so into minus 4. Okay. So, essentially, so what we have done here is that, so now if you look at this, okay, now just take a step back, and if you look at this, what we did here, our main job was to use the Taylor-Maccol theory, solve this, okay, and get the properties in this space as well as on the surface of this cone. So, what we have done is we have drawn several radial lines. We started from the shock, okay, from the shock using this theta s, and the corresponding y I and vr dash is known to us over here. Okay. We started from there, and now what we have been able to do is that this function y here, the function y, which we defined as this. So, d vr dash d theta, this y. Okay. So, if what we have been able to do is calculate that at this point as well. Okay. So, we started from here, we calculated that, and we get this. So, now therefore, now we know the value of y theta s from here, and hence we can calculate other values. And now the next step to do to come here would be again to repeat all these steps, right, all these steps, instead of now this becomes the I, okay, and this becomes your I plus 1, then you integrate, we come from here to here. So, therefore, theta I when we started was theta s, and we moved from here to here. So, now again we will start and do the same things, but starting from here and moving to here. So, moving between theta s minus 4 to theta s minus 8. Okay. So, okay. So, basically y is therefore obtained. Okay. So, y is obtained here. Okay. So, which is d vr dash d theta, right. So, this is my v theta. Okay. Essentially, y is nothing but my v theta, which becomes known, right. So, what we need to do is get vr dash, and how do we get that? So, when I do this, what I get from here, so essentially this y, okay. So, y out here is this. So, when I do this, when I get a solution from here, what I essentially get is V theta dash. So, once we get V theta dash, we need to get V r dash. Okay. I will basically just integrate this. So, V r dash is nothing but correct. Okay. So, in this case all we need to do is V r dash we will get as V theta dash into delta theta, that is all. Okay. So, once we do that, so that is it. Once we do this, so what we know is V theta dash and V r dash at this particular radial line. Okay. So, once we know that, okay, so what else is there to do? So, let us see. Okay, I will come back, I need that equation. So, let us say I erase this part. Okay, so if I do that, so therefore what I get V dash right. So, once we get V theta dash and V r dash, what we get is V dash. So, in this case what we have calculated is V dash on this radial line, and if you remember, let me write this down one more time. Okay. Now, this V dash okay. So, therefore, once we get V dash we can get the corresponding Mach number. So, what we can now get is the Mach number, say V dash I and Mach number I, and once we get the Mach number I, so from here basically if we will get say V r dash I, V theta I, let us write it this way. Okay. So, what we get is I. Okay. Hence, okay, rather in not I actually. So, let us say I plus 1, right. So, this is my I plus 1. Okay. So, now that we have this, so if we have this, then of course, we can calculate the properties. We can calculate all the properties, temperature, pressure, density, etc., because now we have the Mach number. Okay. So, that is it, that is basically the solution to this problem. Okay. So, this was the so as you can see here, so basically what you can see here is that the best way to implement this is using a computer program, right. So, of course, I mean nobody is going to do this by hand, it's going to it's exhaustive numerically. So, essentially this has to be implemented by writing a small computer program. So, if you do this, okay, then what you can take more and more numbers of these radial lines, divide this theta into more lines, and then that gives a better estimation of properties in this region, right. So, the numerical aspect of Runge-Kutta method is this. Okay, it's pretty straightforward actually, and what basically we are doing is using the Runge-Kutta method. Okay, using the Runge-Kutta method, we are actually solving the Taylor-McCall, the Taylor-McCall equation at each and every radial line. Okay, and calculating the property, calculating the V r dash and V theta dash, and hence V dash, okay, at every radial line. Okay. So, Runge-Kutta is the procedure with which we are basically solving the Taylor-McCall equation. Okay. So, now if you implement this, okay, if you implement this using a computer program, let us just look at some of the results that you might get. Okay. This is something that I think you should do as an exercise and see if you agree with me. Okay. So, let me just sort of give you, because now again we have done the 2D part of this, right, 2D wedge. So, we kind of have an idea, we have a theta beta m relationship. So, we know that what sort of a cone angle, what the relationship basically between the cone angle, the shock angle and the Mach number, right. We have the theta beta m charts. So, how would that look for a cone, right? Now, essentially for a cone the shock is weaker for the same theta c and for the same Mach number. For a 3D cone the shock is weaker than that of a wedge. Okay. So, anyway let us look at just you should be able to get properties when from your numerical values, and then you should just sort of cross check. Okay. Now, say we have this. So, essentially say this is theta c, okay. This is in degrees, okay. Theta c, and this is theta s, this is also degrees. Okay, this is not going to be not going to be to scale, of course. Okay. So, if I do this, okay, so then what happens? Say something like that. So on and so forth. Okay. So, say this is say Mach number, say let's say something. Okay. Okay. So, this is similar to the wedge. This is similar to the wedge, and it's just that these numbers are going to be different. Okay. Okay. So, this is your theta c max. Okay. So, now essentially again you can see that for a particular theta c and for a given Mach number you actually have two theta s's. So, basically the strong shock and the weak shock. The weak shock is more common. Okay. So, this is similar to the wedge, okay, but the numbers are different. Okay. And again if you from the numerical solution, if you solve that, okay, now you will see that if your theta c or the half cone angle, if this is say for Mach say 1.5, okay, so this is the corresponding theta c max, right. This is the theta c max. So, now say if you have a Mach 1.5 flow, right, and you have a theta c which is larger than this corresponding theta max, then you will not have any solution. The Taylor-Macol equation is not going to give you a solution past it. Okay. So, essentially after this the shock is detached. Okay. So, Taylor-Macol equation is going to give you solutions only when your theta max out here is less than, when your theta is less than the theta max. So, this is also like we did for the wedge. Okay. Now, also basically the cone, the allowance of the cone for the theta c, okay, the cone allows a larger theta c for an attached shock. Okay. What I mean is that for a given Mach number, for a given Mach number, for the cone, the shock is going to detach for a higher value of theta c compared to the wedge. Okay. For the same Mach number, okay, for a smaller value of theta c, the flow is, the shock is going to detach when it comes to a wedge, right? Whereas for the cone, for the same Mach number, the shock is going to be attached for a larger theta c. Okay, so if I were to sort of do a bit of a comparison, okay. Okay, I can. Okay, we just no shock. It's fine. So basically, say so essentially, if I were to draw, this. Okay, so this is the shock wave angle, and this is the cone angle or wedge angle or whatever, right? So therefore, at the same Mach number, right? So we have, say, a theta max here, okay, and let's call this as 1, and we have okay. So if as I just said that for the same Mach number, so say that for the same Mach number, say this is for say 2. Okay. Now for the same Mach number, okay, the cone has a larger theta c max compared to the wedge. So if you were to look at this diagram here, which would be the cone and which would be the wedge? It's easy to see, right? So what you can see here is that this plot, okay, or this I'm just drawing the half of it, so that curls up. Okay, so for in this here, this you can see has a larger theta max for the same Mach number compared to this one. So essentially, what we're saying here is that this is the cone. Okay, this is the cone, and this is the 2D wedge. Okay, so therefore, if you have for the wedge, the flow is going to detach. For the wedge at Mach number 2, the shock is going to detach at theta max 1. Okay, and for the cone, for the same Mach number, the shock is going to detach at a larger theta max, which is theta max 2. Okay, so well, that would be kind of we'll pull the curtains down on our quasi 2D flow or 3D flow that we started with. Hopefully, when we have a little more time, maybe we'll go ahead and do further, not quasi 2D, where we will actually have an angle of attack and 3D flow, and we will see the physical differences between the two cases. In this case, just one bit, before I close this. So essentially, if I were to just plot this out, okay. So this was our 2D wedge, okay. This is our 2D wedge, and so then we have, say, a shock here, and I am drawing the same thing, okay. Say I'm drawing the same thing over here for the cone, okay, and again I have, say, a shock wave, okay, and again this is theta c, this is theta s, this is your beta, right. See, if you were to look at these two pictures, just to visualize this, this is in the plane of the board, this here. This here is in the plane of the board. So, this is a 2D picture. What you see over here is that this is actually curling away from the board like this. This is a 3D picture of this. So, you actually here what you see is just a section of it. If you cut a section through the cone, then this is what you will see. Okay. So, in here the difference is that although I am drawing it on the board, essentially this is curling away from the board like that. So, therefore, that makes it 3D. So, okay, we will stop here and continue with 3D hopefully with a little more time. Thank you.